Okay, so last time we talked about the horizontal shear flow, and we used that to calculate the shear force that will have to be taken by certain connectors that would connect pieces of a beam together so that they behave compositely. We also talked a little bit about composite action and sort of what that means. Today we're going to move beyond that a little bit. We're still going to use the shear flow, little q equals VQ over I, but we're going to do it now to estimate the vertical shear stress, right? And let me just remind you, if you go back, I think it was like 2 lectures, one of the things that we talked about, let me draw them in the positive sense, when it comes to stress, right, this was our positive sign convention for stress, like that. And what we said was that both of these shear stresses, both the horizontal one and the vertical one, were both the same, tau xy. And the reason we could say that is because if they weren't the same, this cube would be spinning, right? It would be out of equilibrium. So 2 of these, right, are trying to spin, let's say the vertical ones are trying to spin this in the counterclockwise direction, right? So they're trying to spin it in that direction. And then the horizontal ones are trying to spin it back in the other direction, right? So those will always have to be balanced. And so we dropped this idea of tau yx because since they're always the same, we just said, okay, well, we're just going to call them tau xy. So if we can calculate the horizontal shear stress at any point, that also equals the vertical shear stress at that point, right? And so that's exactly kind of what we're going to do here. So this is an example of a rectangular beam, right? So we're going to consider the width of B. I'm going to say that C is half the height, right? So this is a rectangle that has a height of 2C or H, right? And then what I'm going to do is I'm going to make a cut here at sort of a generic location, right? And then I'm going to dimension this, right? So up to that cut, we're going to call that Y. And above that cut to the top of the beam, well, that's just going to be 1/2 times H minus Y. Okay? And then the area above that cut, which is this guy here, right? So this guy we're going to call A1, right? And that's, of course, going to be 1/2 H minus Y, that's dimension, times B, right? And then the last thing I've got to dimension here, and I'll just do it in red, is this dimension here, right? And so this guy we're going to call, D, right? And that is the dimension up to basically the centroid of the area above where I'm making this cut, right? So I'm making this cut right there, right? Then the area above that we'll call A1, and the D, we'll call it D1, is the distance from the neutral axis to that cut, okay? All right, so now we can start to calculate. So this is our little q equals big V, big Q over I, right? So let me pull out this Q, right? It should be pretty straightforward. This is the first moment of the area, right? So this is 1/2 H minus Y. So that's the height of the light blue area. B is the width, right? So this guy right here we call A1, right? And then I'm going to multiply that by 1/2 times 1/2 h minus y, okay? And then that is plus y. So this guy here is d1, right? So that there is the height of the light blue section. I multiply that by 1/2, right? So that gives me the distance between this red line, right? It gives me that distance there, right? And then I simply add y to that distance, right? And that gets me from the neutral axis all the way up to the centroid above the cut. Okay, and the cut is where we're trying to solve for the shear stress, right? Now, if you notice, I've parameterized this. So actually what we're going to get here is the shear stress as a function of y, okay? Shear stress as a function of y. All right, so if I work this out, right, I will get that Q equals B times H times C squared divided by 3. Right? And you guys can work that out on your own if you want, right? But it's pretty straightforward, right? So, oh, wait, hold on. You know what, sorry about that. Let me redo this. That actually is I. I was wondering why it wasn't a function of y. I was just looking at the wrong line in the notes. So this will be BH squared divided by 8 minus BY squared divided by 2. And that's if you just multiply all of that out, right? And then if we substitute in that C equals 1/2 H, we get that this equals BC squared over 2 minus BY squared over 2. And so that's Q. Like that, okay? So that's Q in terms of B, C, and Y, right? So those are basically the dimensions of the cross-section plus plus this coordinate that we're defining, right? So I plug in y equals 0. You'll see Q is a maximum then, right? Because any other thing that y equals, it gets subtracted from that first term, right? But at y equals 0, so that would be the neutral axis, I actually have a maximum of my shear force. Sort of interesting. So where the bending stress is a minimum, the shear flow, and ultimately, as we'll see, the shear stress, which are proportional to Q, are maximums at that location. Okay, so I'm still in red, so let me go back to blue. So this guy is, I is now BH cubed over 12, right? And that equals BHC squared over 3. Right, again, because C is 1/2 H, right? So I can plug that in. Right? What did I do there? I guess we're keeping one of them in terms of H. Okay. Probably had a reason to do this. I made these notes up about a year ago. Some things I notice as I'm going through. Okay, so now we can just simply plug those guys into the Q equation. So that's V times this Q here, right? So that guy is BC squared over 2 minus BY squared over 2, right? And then the denominator is that I. Actually, here's exactly why I did that. So I have a BH, right? And then this is C squared over 3, right? And this BH is just the total area of the cross-section, right? So that's the, B times H or B times 2C, right? So that's the total area. And if I try to simplify this now, I'm going to get that Q equals 3 times V over 2A times B minus BY squared over C squared. Right. So that's my Q. Now, if you notice, all we've got to do to translate Q into shear stress is I've got to divide by the width. Right? So if you think about shear flow is the force per longitudinal length. Right? So if I want it per longitudinal area, right, I've already taken the length dimension into account. Now I've got to take the width dimension into account. Right? So tau xy, which is our shear stress, is going to be Q divided by B, right? And that is going to be 3V over 2A times 1 minus y squared over c squared, and that equals my tau xy, and I will box that guy. Like that. So now we can plot that, right? And we can see how this looks. So let me redraw my cross section. I'm going to draw it a little bit bigger this time. Right. So that's my neutral axis. This dimension here we're calling C. This dimension here, the width, we're calling B. And we're taking the Y dimension from the neutral axis positive upwards. Right? And the V is the vertical shear stress, or the vertical shear force. So that's V. And then the only other thing I want to do is I'm going to try to show it as a dot. That is the area. So the overall cross section, right? That's the area. So this is going to equal B, 2BC, right? So let me just clean that up a little bit here. So C is half the height, so the total height is 2C. B is the width, so 2C times B is the total cross-sectional area. Right? So if I'm now going to plot this, I didn't actually leave myself enough room, but that's all right. So this is tau xy, right? At the top and the bottom, right, so when y equals c or y equals minus c, right, what you can tell is that that term there is going to go to 1. And 1 minus 1 is 0. So the shear stress vanishes at the top and bottom of the cross section, right? So this is where the shear stress is 0, and then at the bottom of the cross section, it's also 0. Right? And then you can see that at the neutral axis, that's where y equals 0, right? So that second term goes away. And now we just have this term, right? 3v over 2a. So that's actually the maximum shear stress, and that occurs at midspan. That's somewhere like here. Oh, I just did a good job of that too. It's hard to draw parabolas. So this guy here is my shear stress distribution. and where this, which is at mid height of the cross section, so that's tau xy max, and that is 3v over 2a. Right? And we could also say that tau xy average, right, is just v over a. Right? So that is our average shear stress, because the total shear force, V, has to be spread throughout the entire cross section A. So the average has to be V over A. So this guy here is actually quadratic, right? And you can see that because the y term is squared, right? That y term is squared. So there's a few things that I think are sort of interesting about this, and we will start to do other examples in the next lectures of, you know, what happens when it's an I section or a, you know, a T section or something like that. But for the time being, with this rectangular section, there's a few things that we can note, right? One is that where the flexural stress is a maximum, the shear stress is a minimum, right? So that would be at these ends here, right? So if I'm going to, let me do this in gray, and I'm gonna, if this confuses you, please just ignore it. I know I say that a lot, but so this here would be my bending stress, right? So if you look where the bending stress is a maximum, right here and right here, the shear stress is a minimum, is 0, okay? And where the bending stress is a minimum at the neutral axis, that's where my shear stress is the maximum at the neutral axis, right? So there's this sort of trade-off, right? What it generally means, and we'll get into this more, you know, in the future lectures, particularly when we start talking about I-beams and vertical shear stress distribution in an I-beam, is one of the things that you could say is that, and I'm going to do this sort of just sort of in a gross manner. So these regions here, right, far away from the neutral axis, those are going to be governed largely by flexure. So those regions are governed by flexure, right? And then the regions in the center near the neutral axis, right? These regions are going to be, governed by shear. Right? Notice I'm not connecting them. I'm not trying to point out that this particular place is going to, you know, definitely have, you know, more shear stress than bending stress or whatever. I mean, some of this depends on material properties, etc. But the one thing you could say, again, for a rectangular beam, is that when you get to the areas that are furthest from the neutral axis, they're going to have a maximum bending stress and 0 shear stress. Right? And when you get to the areas that are close to the neutral axis, they're going to have 0 bending stress and a maximum shear stress. Right? So you can start to look at a beam and start to see what demands that beam is actually being exposed to. And it's those demands that drive a lot of the shapes, right? So the web, that vertical middle piece within an eye girder, primarily takes shear, right? Whereas the flanges, those horizontal elements that are pushed as far away from the neutral axis as we possibly can, they primarily take bending, right? And that's an assumption that is used actually quite often in design. Okay, with that, I guess I'll end this lecture, and I'll see you guys in probably